PhD student. I'm an industrial PhD at Maritime Robotics in Trondheim in Norway. And I'm also associated with Norwegian University of Science and Technology, also in Trondheim in Norway. So I will talk about cameras mostly today, theory and applications. So I guess you can say the key to my work is giving a researcher like Bard as good data as possible to work with their visual algorithms. So the agenda today is I will talk a little bit about the geometry, the basic geometric models, and how geometry is applied in real-world scenarios, and evaluations of the geometric algorithms and so on. I'll talk a little bit about the image sensor, mostly as a background to a project me and Fabio is doing now in object detection, where you want as good signal-to-noise ratio as possible. Yeah, so first a little bit about geometry, the geometric models. So everyone who has worked with cameras and computer vision, they know about the pinhole camera model. Basically what you do is when you have a camera, you get a 2D image in general, and you project points in the world onto this image plane. So it's a 3D to 2D projection. And there are some simplifications and so on. And then also you have the lens distortion problem. Basically, lens distortion is the deviations from a rectilinear projection. So the deviations from this projection. And it depends a lot on the lens, and also, for example, the focal length and is my computer that's making the sounds? Device is ready. Okay, I'll just. Okay. Okay. Also, if you have, for example, if you have used the GoPro, it has a very short focal length, so it has a lot of distortion. And if you have a longer focal length, it's generally a much better, much lower distortion. So you have to handle this when you use the pinhole camera model. So basically, I was in the station keeping trials in Botnian Bay in March last year, where the mission was basically to estimate the size of ice flows around the vessel. And one of the requirements from Statoil was that it should be very accurate. They want a very low distortion. So I did a project then to see how well can we do this, especially if you look far away. I mean, if you look very near on this ice flow, it's not so difficult to see. But if you look very far away, how far is it accurate? Yeah, so experimental data from this. So basically I took some ice flows, because there has been studies on the ice flow size distributions and so on, to see how well that works. But I wanted to do a more close study on some ice flows to really see what limits us. Yeah, this is the line here, not the dashed line, but the filled line. I think it's at 45 or 50 degrees camera to object angle, so not very slant. It's maybe around here somewhere, compared to if it's very far away. I think this is 83 degrees up, the dashed one. So the conclusion was this, is that as long as the ground resolution is enough to separate the objects, the estimation accuracy holds at very slant angles. Yeah, so that was the takeaway. Everyone who went to the Red UAS and saw my presentation, they know more about this, I think. And then I did another real-world application, camera attitude estimation. And as Professor Beard told before, it's a very small error in the angle estimate. It gives a very big error in the position estimate of an object when you georeference. Yeah. So I want to improve this. I want to improve, for example, if you have an IMU, it can drift especially in yaw, because you use the magnetometer and it's a lot of noise and so on, disturbances. So I want to a way to get a better estimate in some images, and you can also use it as a reference, I mean, for IMU to calibrate it. So what I did was to match rendered horizons. And these rendered ones, I render from a digital elevation model, a 3D model of the terrain, basically, with a horizon in a camera image. So this is the 3D model, and this is, I don't know if you see so well, but this is the camera image, and I find the horizon here, and I render it from this one, and then I match them. So basically, there's similar works, and they use quite fancy algorithms. I use a very simple one because I want it to be fast, real time, and so on. And I also want to estimate the yaw, because most people don't estimate the yaw, which is usually also the biggest problem to find with IMUs. So I use shape features. Basically, I do just the mean, and I see how much wrong we are in pitch, and I iterate this to find the error. And I use iterative grid search for yaw. So grid search is a bit slow, but since the other ones are so fast, I can do this, and we can get a very robust yaw estimate. So I did experimental setup. I use a FLIR pan tilt device into my camera, and did very fine steps to see, and I got 0. This is the error in roll pitch and yaw. So it's much better than an IMU, for example. There are some systematic errors, which probably depends on the elevation model. So it's future work to remove those errors. We do a better rendering of the synthetic horizon. This is it was published in the Advanced Motion Control, which is in March this year. Okay, and then I will talk a little bit about the imaging sensor and kind of what you should think about if you want a camera that's good for object detection and so on. And basically, this summarizes it. With every airborne camera, the aim is to achieve the best possible signal-to-noise ratio in order to be able to dot processing to work with data that are as close as possible to the information they contain. So as good signal as possible. So there's the camera equation, where you can see how the different camera parameters influence this. And this conversion from radiance to pixel intensity in the camera, like the image that you get out. So first we have this is the pixel value is proportional to the spectral radiance, which basically depends on the scene, like the object and the sunlight and so on. For example, this is the light source. So you can see it's a huge difference. If you have sunlight, the irradiance is 1,000, and it's a huge difference. That way you get much worse images at night, for example. And why it's the darker it gets. If you want to take photos like in the dusk and dawn, there are much higher demands on the camera than if you want to do it in sunlight, for example. And then there's the transmittance of the optics, how much light passes through. And this is one of the reasons why the optics can get really expensive. And I've seen there's usually a graph that shows the fall off of intensity from the center of the lens and so on, and it's quite big difference. Usually maybe but compared to, for example, this, it's not so much. It's maybe you can get twice as good if you have really good optics. And relative luminance. Again, compared to the center of the lens, the illuminance falls off, depending on the lens, the physics, and so on. And then the F number, which is focal length divided by diameter of the entrance aperture. So this is power of 2 squared. So the focal length and the F number has a big influence. Then the area of the pixel, and it also has a big influence. Like if you have a twice as wide pixel, it's also to the power of 2. And the integration time, the exposure time, It also has a big influence. Yeah, so that's the background to get as good camera, to optimize the camera kind of for object detection or image quality in general. So the goal of the object detection here is to distinguish or subtract the background noise from the object, the signal. And the noise can come from image acquisition process. It can be the camera that gives you the noise, but it can also be the other objects in the background, like trees and so on. So yeah, we need a, yeah, so I have a project here. Sorry for your confusing layout. So we want to detect and classify objects at the sea surface using an infrared camera. And then my work is kind of the image processing part. Fabio will talk later about the neural network part. But I use adaptive background mixture models for real-time tracking is the title of the paper for the background modeling. It uses a mixture of Gaussian to model the background. So basically, yeah. If it's a very highly dynamic background, it's very difficult if there's trees and other objects and so on, a lot of noise. But as Fabio mentioned before, it's an infrared camera at the sea surface. It's not a difficult scenario, and I will show you a little bit how it looks like. So you see, it's very uniform. It's not a projector. It's really this uniform. Oh, sorry. There are some, because this is not a cooled camera. This is not a cooled camera, so there are some irregularities in the image, but since they are kind of the same, like it's darker in the edges and so on, the modeling algorithm takes care of this very well. So we can do some playback. And this is just of the labeling of the data. This is nothing, no fancy algorithms or anything. So we have the boat, and we have a pallet, and we have a human, and some buoy, and so on. That we don't use in the nice tracking algorithms. This is just background subtraction in order to detect the objects. Yeah, it's 11 minutes. I don't think you want to watch a boat for 11 minutes. But yeah, it also has the problem that Brian mentioned before, that if an object is too still, it doesn't. It thinks it's the background after a while. So yeah, I think that's it for me. Any question? No, this is not. This is under. There's a boat, a human, a buoy, and a pallet, basically. Yeah. Yeah. Is the right English word, right? Yeah. Because so we choose the pallet actually quite strategically, because they have a problem with the fishing devices that they attach them to a pallet. And when they do the scanning of the oil, I think, they need to like interrupt their operation if there's this fishing device. So they want to be able to see them. Yeah, exactly. Yeah. No, oh, sorry. I should have explained this. Yeah, it's on a fixed-wing UAV, actually, so it's moving quite fast. Mm. In general, yeah, but since this